Quick announcements. Last few days today. Exam is tomorrow morning. So as usual, I think Akiva's available in the morning before class. So Akiva's here with us today to be able to answer some questions about the latest lab that was assigned yesterday. But I wanted to go over it real quick before I set you loose to get started with it so that I can answer some questions about it. And Akiva's also here today to answer some questions about it. So let's start there. We'll start with this, then I'll ask for questions about the study guide, and we'll go into the remaining examples that we were working on yesterday in preparation for the exam. Any questions or concerns before we describe assignment? Okay. So this is the most involved assignment I think we've had so far in here with regards to the requirements, but it is also a bit more structured. So those of you who like structure in your assignments will probably appreciate that. It took a little bit to bring all of this together, which is why it's been delayed a little bit, but I think the end result is worth the wait in that the outcomes from this assignment will be very good for people. As I mentioned yesterday, I very much want there to be some project that you take away from any class that I design, and this will be that main project that you can showcase. So we have a bit of a premise here, a reason why we might care about sparse or dense graphs. So if you were a game developer working on a character-driven RPG, you would have a couple of different kinds of relationships with characters in the game. You would have exactly what your relationship is and what this character thinks of you. One of those is going to be sparser. You don't necessarily know everybody in the game world or have a relationship with everybody in the game world, but everyone in the game world has some opinion of you. So the entire idea of this is that we do that, but we store it in some kind of interesting structure. So in this class, we haven't really taken advantage of a lot of the prerequisite content that you've covered in past classes. So I wanted to bring back a lot of the inheritance that you saw in 211 and apply that to a more data structure oriented, kind of taking 211 and 300, combining them into one project, and then we'll throw the algorithm on top of it in the next part of this. But to do that, we're going to introduce you to one of the design patterns, something that I'm very aware of, given that we don't have our design patterns class at the moment, and we haven't yet roped it back in, as I want to get people experience working with design patterns. So the pattern that makes the most sense for this assignment is the facade. I can go into this in a bit more detail as people would like, but there's also some information here at Refactoring Guru. Those of you who have seen that before, it's a fantastic resource for anything design patterns, refactoring, code smells, things to not do when you're writing code. So Refactoring Guru is a super useful resource that I use in a lot of my design related classes. But this will introduce you to the concept of the facade. But then we're going to use it as we create our own custom graph structure. So as we learned when we introduced graphs, there are two different ways to store graphs. We can either use an adjacency matrix, which is a 2D array, or an adjacency list that is a list of linked lists. And so we would want to be able to store either kind of graph, especially in this example where there is a sparser graph and a denser graph that we're going to need to be able to represent in this RPG. So we're going to have a little image here of what the structure of this looks like. But let's basically say we're going to have an API superclass, the DW graph. This is going to be.
Well, you describe it, I can draw it for you.
Yeah, that works. have a color preference? Get a color. Yeah, so we have an API driven superclass that's meant to keep track of the API and make sure that we can use the same API with every subclass from this. So underneath that, we have our digraph object that is just an interface. And that's going to give us everything that we want to be able to do within our two instantiations of a digraph, which are going to be our adjacency matrix and our adjacency list, the two different ways that we could store that graph. So the purpose of this layout and this structure is that the same API can be used no matter which instantiation of a graph you are using. So I should be able to use the same calls, the same methods from a driver's perspective, and not care about whether the underlying representation is an adjacency matrix or an adjacency list. That way you don't have to have two different APIs and you have to know as the user, am I instantiating an adjacency matrix or am I instantiating an adjacency list? From the outside perspective, that's an implementation detail that they shouldn't need to worry about. So the design of this facade is saying that we can interact with this through the API without worrying about the underlying representation. And then from our perspective, the designer, we worry about the underlying representation so that the end user doesn't need to worry about the underlying representation. So a benefit of facade in general, as Akib is writing, is the API is stable, which just means that it's the same API that you use regardless of the underlying implementation of the object. For those of you who are remote, I'm going to this over so that you can see this as well. That's as far as this goes. So it doesn't keep going. Go, camera, go. Believe in you. There it is. One other aspect of this that is going to be important is the fact that it could be that these underlying graphs change as you are using them. So we are allowing for the ability to add nodes and remove nodes from a graph. And as we do this, you may change the desired underlying storage structure that we're using as we start with a sparse graph. So we instantiate an adjacency list. It could be that we add enough edges that the graph becomes dense. So as that happens, it may be worth converting between an adjacency list and an adjacency matrix while keeping the underlying API the same. From the end user's perspective, they don't know that something has happened. They don't know that we instantiated a 2D matrix and now have filled that with the same information that was stored in the list. They don't know that that happened. In the same way that if you're using an array list and underneath the hood, you've added enough to that array list that it needs to resize itself, you don't need to know that from the end user's perspective. It's just something that happens underneath the hood. For all intents and purposes, it's still just working. But the implementation detail underneath the hood is that we've doubled the size of the array and we've copied over all of the elements from the old list to the new list and making it larger. So from this perspective, we're doing something very similar. You will be implementing the ability to convert between the matrix and the list when you think that it is relevant that you've gone from a sparse graph to a dense graph. Questions?
So we're gonna need to come up with some sort of threshold for density.
Yeah. So part of that will also be if you put that threshold for density, what happens if I add an edge and then remove an edge and then add an edge and then remove an edge? If it's the same threshold for converting between the matrix and the list, you may be converting with every single add and delete if you're right on that threshold. So typically what's done instead is you put a threshold for converting from a list to a matrix that is something like if there are 60% of the existing edges that could be. Now, that definition is we've moved from sparse to dense, but the same thing in the other direction would be true at 40% instead of 60%. And that way you need to add or remove 20% of the edges in the worst case before you're going from a list back to a matrix, back to a list, et cetera. So you're not doing that transition because it's an expensive computation to take everything from a list and put it in a matrix, everything in a matrix and put it in a list. So you don't want to be doing that with every single insertion or deletion from the graph. So have a different threshold for converting one direction and the other direction so that maintain complexity. Yeah.
And do we need to optimize that?
Not necessarily. There are certainly ways to do that, but it's not built into the specifications that you absolutely need to. Always be looking for, in the worst case, it's like make it far enough apart that you're not doing it on every single insertion. If I bring it up.
48 points extra credit. That is a lot.
Yes, and the reason is, so one of the outcomes from this is just getting experience with using a facade and seeing why a facade is a useful design pattern to implement. It allows for extra scalability in this way that, let's say we wanted to add a third way to store an underlying graph. In addition to a matrix or a list, there was some third structure that we eventually wanted to add. We could do that without changing the underlying API. From the end user's perspective, they would just see new feature. You can store this third graph storage type, but nothing else about how they interact with the code that they've already written would change. Does that make sense?
Yeah, there are basically two extra credit options. You get to pick one. They're both pretty easy. So one of them you go up and use the facade. The other option you can go down and you're adding a new implementation. So you're not going to need to really touch the diagraph at all for the extra credit. You're either going to implement a purely node-based structure as an exercise on why we actually do it with the lists, is to experience what that node-based structure would be implemented as and how much of an aim that can be. The other direction, you go up and you're making two new facades without touching the diagraph at all, because you can manipulate how the facade interacts with the diagraph and get new graph structures. So the one that we're building for the primary assignment is a directed weight graph. So all of the edges have directions, all of your edges have weights. But there are other common versions of diagraphs that may have different specifications on their edges. Like some of them are purely symmetric. Some of them don't have weights at all. So you'd pick two new types of graphs and manipulate the inputs in from the facade to get two new graph structures without any extra logical base code.
Yeah, so this is one way to make up the fact that there is so much weight in assignments in this class. So if things have been not going quite as well as you would hope with regards to assignments, this is an opportunity to do something useful and difficult, but also get some credit back for it. Questions on this layout or the concept of the facade? I just kind of wanted to go over this so that you had the context that you needed to start thinking about or getting started on this. I anticipate this is going to be a lot for some people, for a lot of people. So again, office hours, I'm very happy to meet with you and help you get started. Any questions from anyone remotely before I switch back to what I'm projecting? How are people doing? How do we feel about the idea, at least the concept of the assignment? Does everything there make sense? Is there anything that I can clarify?
Makes sense enough to me at least, not sure about everyone else. I'm not, but yeah. Just gonna try my best at that.
Okay. So there's a lot more to read and look at, but there is a pretty good API in existence here. Please do follow the API. Make sure that everything that has a name is named the same thing as it is in the API.
I do want to point out, I'll update the file as soon as I get back to my desk here. But we did want to have the adjacency list implemented as a double nested hash map because of how common this structure is as you continue on in computer science. That's probably my most used data structure right now.
That's not exactly one I'm the most familiar with.
So if you have a hash map, you have a key value pair.
Oh, yeah, now I remember.
So a nested hash map is going to be that the key is a hash map. You have an outer hash map that has a key value. Sorry, I meant value. The outer hash map has a key. That key leads to a value that is another hash map. That is a key value pair. So an adjacency list in this case is a list of linked lists, but we think of the linked list there as a hash map because we need the ability to now store which vertex name is associated with the. When I say the structure that's at row 6, what does that mean? Which vertex is that? We don't know unless we have some string representation here of what the vertex is called.
In general, anytime you're dealing with something where you want to look it up by a key, you want to try a hash map implementation.
So again, happy to help you get this all set up or to visualize what this actually means or what it's doing. But I'll save that for office hours.
I helped build the assignment, and these are all structures I'm super familiar with, so you're always free to message me. Canvas on Discord, email.
Thank you. I really appreciate that.
Want to make sure you have the support to do this. We know we're challenging you pretty significantly, and we wouldn't want to do that unless we could support you through it so that you can actually take something away from this and not just struggle and then submit the best results of that struggle.
Yeah, I'm definitely confused by the double nested hash map, because I thought that the point of the adjacency list was that you're storing pointers to the actual vertices. Not how that's.
Yes, but then we would try to say, all right, is there a connection between vertex C and vertex D? Where is vertex C in your list of adjacency? In your list of, how do we know which one D is? We either need some kind of comparable lookup list that allows us to say, given the index D, return an integer that is the index into, and that itself is a hash map, where the key is the name of the vertex and the value is the index into the structure that it is. So if you're doing that, then you might as well embed that hash map as the lookup, which is the outer hash map here.
Hash maps allow you to also iterate through key value pairs. So when you're thinking about it, this outer hash map is going to be storing your source key. So if you're like, I want to know what nodes, this like node A is connected to, you can get all of the inner hash map entries on A. It will tell you, node A is connected to node B with the weight, 5, and node C with the weight Or you can look up hash map. And then hash map, you can get both keys at the same time. It will just spit out the one double that is the weight for the edge from A to B. And the reason we're doing the object double for the weight specifically is because it's nullable. So that way you can return null if an edge does not.
There's a lot to this.
Hash maps are a very useful structure, but I don't see them very often before algorithms, so it's an important one to get.
Anything else I can answer? Or Akiva can answer? Okay. I think people can get started on this or get started thinking about this, and I'll collect a list of questions that I hear, and as I hear questions from people, I may follow up and come up with something else in class to describe. But I'll let you get started and get stuck and come to me with questions, collect those and move on from there. This portion, yeah,
Wednesday, 2 weeks from now.
the entirety. This portion though is due next Wednesday, right?
I said this portion will be due in,
Yeah,
that way we get one extra week.
I also did look at it and check the due date, and I went through the entire document, briefly. And didn't exactly have any questions to ask yet, but yeah. And sure. It definitely speaks the truth.
So if this is set for 2 weeks from now, that'll give us one more week, that'll be middle of week 10. I do want to do some assignment on NP completeness and reductions. That will probably overlap something somewhere in here. So we're looking at a somewhat busy end of the quarter that may end up being due over finals week as well. Just there's not going to be a final in here. That last exam will be that last Friday of class.
Oh, okay.
So there may be one last assignment that has you working over finals week instead of there being a final.
Wow, talk about the second quarter in a row. I don't have an official final in one of my classes, and at least this time it's completely in person. Well, hybrid mainly, but yeah, the last time that happened was, let me think. Oh yeah, Technology World Civilization last quarter. And I did that completely on my wife. That is not important right now. Sorry. Question.
So our last exam will not be.
There may be a couple of tying everything together comprehensive components, but it wouldn't be a question that I could have asked on any of the individual exams beforehand. So I'm not going to have you do a recurrence relation on the last exam. I'm not going to have you trace Dijkstra's algorithm on the final exam, but I may have you look at everything that we've looked at together and say, given everything that we've studied, when is this concept that we've studied valid? Or when it's just something that ties the reason we studied all of this together. And some of that may rely on an understanding of some of the prior material, but the target will be kind of tying everything together, not this specific part of this thing that we covered at the beginning of class. You should remember that. Anything else? Okay. Thanks for drawing this out. I think the visual helps a lot. Yeah. Thank you, and we'll get back to our regularly scheduled review. So last time, we were in the middle of this problem. What have we thought about? Did we come up with a solution for this? So it looked like from the examples that we saw here that the right answer was always to surround everything except for the first number with parentheses. That's going to be what minimizes that value. And then when you divide something by a minimal amount, you get the maximum amount. Was there any exception to this logic? They do have to be integers.
Yeah, but. Thing. Else, actually, I'm not really sure of the answer. Yeah, well, a mathematical logic at least makes sense to me.
You want to go out on a limb and take a guess?
Larger numbers. Right. I think it's Eric. Oh.
Yeah, so in the first case, we have larger numbers, larger numbers, larger numbers on the left. And on the right, we have larger numbers always on the right. So if we alternated those, does that change anything? There may be a nested problem in here.
Maybe.
If that were the case, what would a greedy assumption be that we could take? If we look at two numbers and we see that, or maybe a window of three numbers, if they're always increasing or always decreasing, we can just continue that process and expand that so that we can throw parentheses around that sub-expression.
Okay.
What's the dynamic programming part of this? How could we break this into something that's dynamic programming?
Already related vision concern.
Yeah. Yeah, we've stored the results of certain division. If we had a solution for a sub-expression, so imagine the sub-expression for example 1 is 100 divided by 10 divided by 2. If we figured out the optimal way to do that division, how does that help us with 1000 divided by that answer?
1000 divided by.
Does that make sense? If we had already calculated the optimal way to do division, then it would be a lookup. So with dynamic programming, we would want to store that and look at starting at the subproblems. As soon as you have a single number, it's obvious what the answer to just 1000 is. So we could do that. I like it. I think it's solid. Questions on breaking this down into dynamic programming, questions on thinking about a greedy solution?
I have troubles with like going through the list of steps of dynamic programming.
Mhm.
It's easier for me to just see thing that I do and be like, watch a store that.
Yeah,
But like, I guess that's like the only. I don't- I'm not actually good at it. Okay, step one is this programming.
yeah. I find following an exact sequence of steps to be a little bit overrated. It's important to know when your intuition is going to lead you astray or when there might be limitations to what you're considering. But other than that, the steps are there to guide you to create an intuitive process where you look at it and see the subproblems. So if you look at it and see the subproblems, I'm fine with that.
I didn't know like what the exam I'm expecting. Like, if I can just look at the problem and be like, oh, let me just store everything that I do and then
Yeah.
just reuse it.
As long as you can show kind of what those subproblems are, what is it that you're storing? What is the process to break down a problem to be able to look at the possible solutions? It's just taking that idea and formalizing it.
Add any number.
So I guess you're not really looking for us to like literally go through those steps. You're just like,
Not necessarily. I'm going to look at your thought process and determine, are there any issues with it? I don't want you memorizing steps. I want you building an ability to break down a problem you haven't seen before and come up with an optimism. However it is that you do that. Do we want a fourth example? Is there anything to do with this third example? Do we feel like we understand how to break it down, dynamic programming, what a greedy assumption might be? We haven't really answered the question as
No.
of does a greedy question, does greedy work here?
we have to like find which cases.
Yes.
I don't know. what they
Yeah,
are.
there are some problems in here that will make a difference.
Yeah, we have like a certain lineup of numbers of.
My view of this is there is not really a good greedy assumption we can make.
No,
Don't we just always want to divide as long as we can divide the denominator one more time? Like I just look at it as you want the biggest, the smallest denominator.
Yeah,
For the maximum number, so every single time since our constraints are 2 to 1,000. No matter what, if there is another value I, like we always want to choose division. Until we get to just
that
a
is
numerator and a denominator. We don't do anything with the numerator, but we're just always going to divide.
yeah,
the
by the largest
denominator.
possible denominator that we can.
So we're adding as many parentheses.
This is a good example of something that we should, I don't have an example prepared in front of me for whether that always works or why that would not necessarily work. But I think that's a good problem to explore for studying for this is there a counterexample to that idea? Is there a way that we can structure this such that it's not always the right answer to throw parentheses around everything except the first number? That's that kind of intuition building that will eventually lead you to be able to see a problem like this and just have an answer. If it's not intuitive to you as to whether there's a counterexample to that, that just means that there's a little bit more work to do.
It means in just do this one thing every time.
Yeah. We're thinking about a possible greedy solution. Are we analyzing the overarching patterns throughout the examples? Yeah, if there's a greedy solution, we want to find the pattern that is what is the sub problem. And if the sub problem can have the exact same greedy solution applied to it, and that works all the way down to the base case, then we can say that this has a greedy solution. But there needs to be a single sub problem remaining, and that sub problem needs to be another example of the problem that we have, and then we have to show that by solving the sub-problem, we've solved this one problem with that same assumption. It turns it into basically just iteration. All right, I do want to go through one more of these since we're running out of time a little bit, but here's the last example. What do we want to do with this? Get in about, it's too far. Just a little bit. You got this. Go too far. Better. Not better. Right. Is that readable remotely? Probably not. Whenever I try to zoom in, it zooms in too much. Yeah. I actually can't paste the slide image into the chat because the machine that I'm running this on and the machine that I'm running Zoom on are different. So one thing I can do, at least in the short term, is I can do this left side, right side.
Only one repeated value is not okay.
There we go. That is true. This is on campus.
Okay, I suppose it's or the value of man.
How's this doing? Does the problem make sense? So we're given two sorted arrays, so we don't need to worry about anything else other than is the number present in both arrays.
I could.
For any number that is present in both arrays, we can teleport between them. We'll start in one array and just start adding every value we see as we go index by index. Whenever we hit a number that is present in both, we can hop between.
You hop to the other one, you don't, that valve again, do you?
Correct, you do not get that value.
Oh. Okay.
Like for me. Feel like you could use programming rather than greedy.
Definitely.
Like I feel like we need to be able to look at everything before you can.
Yeah.
Yeah.
So if we could, with a single pass over this, find all of the overlap points. So the first overlap point in this example is 4. It becomes pretty apparent from there which array to start with. What is the best sum of values before 4 in each of those arrays? In one case, we have a sum of 2, and in one case, we have a sum of 0 before we get to that first overlap point. So we should start with the array that has the higher sum. When we get to the 4, we have the option to switch or not switch. Whether we do that or not isn't important. What becomes important is maximizing the sum before we get to the next overlap. So we could, from here, calculate the sum before we get to 8, which is just 5. And from here, we can calculate the sum before we get to the next overlap, which is 6. We should take the maximum of those two, 6 rather than 5. Get to this point, this is a potential overlap. So from both arrays, whereas what's the sum before the next overlap? There is no further overlap, but 10 is greater than 9. So that tells you what to do at each one of these now discrete steps.
Would it be the same if you just stopped at 9?
What do you mean by stop at
Like,
9?
the same amount. Or is it?
Yeah, I think I know what you mean. We would want to go back to the 10 is greater than the 9. So we would have to, we kind of carve this into call it this component, and we look at, actually I should draw this more like that. So 2 is greater than 0, 6 is greater than 5, 10 is greater than 9. So that tells us since 2 is greater than 0, start here. Since 6 is greater than 5, flip. Since 10 is greater than 9, flip. And that tells us the entire path with one pass. So I picked this problem because at first glance, this looks like the best we could do is probably just dynamic programming. But there is a greedy assumption we can make here. And that is that this is exactly the same problem as one that both of these arrays stop at 8. And it's the same problem that both of these arrays stopping at 4. And so you can discretize this into its individual components and then stitch them together to create the solution. So the single subproblem that remains for a greedy solution is these exact same arrays, but cut them off after the last time they share something in common. Cut that off the last time they share something in common before that. So by solving a single one of those subproblems, this subproblem that's left over after that is its own problem that has the optimal solution to the first part, plus this unknown second part. Then you just repeat that, you turn that into iteration, and you have a loop that finds this path. Does that make sense? So if we're implementing this, we're going to come up with probably, I'm going to store 2 arrays that are the indices of the overlaps in each of these arrays. So I'm assuming this is 0 indexed. The overlaps occur at 1 and 3. And here it's at 0 and 2. So the first problem that I would say is we know they're going to be the same number of overlaps between them. So the length of this array should be the same as the length of this array. That means that there are pairs between this that represents the indices that have the same value, and this is the indices that have the same value. So if this is the case, then I say, is the sum from 0 to 1 of this array greater than, less than, or equal to the sum of that? And honestly, since this is the number we don't really care about, we could just Turn this into that. Doesn't really matter which one we do. I don't know. Are people familiar with interval notation?
I'm familiar enough with it.
This means at this index, so including this index, a parenthesis means not including that index. So this sum here is 2, this sum here is 0. Whereas if we replace these with square brackets, then we're including that last index. So this sum would be 6 and this sum would be 4. 2 plus 4 versus 4 versus now we're ignoring the 4 is 2 versus 0. Back in at the end, yeah. So if we do this, then we see 6 versus 4, but we see the 6 here is better. So that tells us start with this list. So it says add this 2 plus this 4. And then we can move on to the next interval. So we want to now not including 1 or 0 anymore. We want to get up to 3 and up to 2. So that would tell us take this value 1, add 1 to it, put it here. And go up to and including that value. From here, take the right value, add 1 to it, that becomes the new starting value, and go up to and including that. So 2 plus 3 is 5 plus 8, which is 13. And here we have 6 plus 8, which is 14. Since the lower one is larger than the upper one, we should switch here and go there. So this is going to say 2 plus this 4 plus this 6 plus this 8. Then the last value here would just be saying going from the next number up to the end of the array. So we would say now going from 4 and 3 up to the end of the array, which we can say just by comma that says to the end with Python syntax. And so since now 10 is greater than 9, this would say go back here, ignore this 8, and incorporate the 10. So this is a greedy approach because every time there was a single subproblem left. When we calculated this, it didn't affect anything for later. So we just ignore the route that we taken, the path that we taken to get to that point. And between these values, we're just looking at these nodes. It has nothing to do with what came before it. So the overlapping subproblem part of dynamic programming would be if we did care about these, the kind of the history of this. The greedy assumption here just basically says that the history doesn't matter. So at least this is my view of how to start with a problem like this and go through and find a solution. I wanted to make sure that for at least one of these, I fully drew out my thought process. I think there are some other of these are good for you to go practice with.
Yes, definitely. I'm not entirely understanding enough either, but I am trying.
Believe in class that we finished the broken calculator example.
Yeah, very back at the very first one.
Yeah, well, we did not finish that.
Yeah, let's see what I can move through. So, did anyone get a chance to think about broken calculator between yesterday and today?
Unfortunately, I didn't, unfortunately.
So to me, this is despite pulling this from the greedy set of problems, it's greedy in that you can get reasonably close to the correct answer, but the actual correct answer, in my view, is relying on dynamic programming. And the reason is you can't actually calculate this in a greedy form. It's a little more complicated. It depends on the distance between. It's gonna take me longer than a minute to draw this out. But if our target is significantly lower than our, you want to get to 0. We want to get to something that's just under a power of 2. If we double and double and double at the beginning, we get to 6 and 12 and 24 and 48. Once we get significantly over this value, there's a lot of decrements to go through to get to that point. But recognizing if we pull that decrement one before, it's the equivalent of taking 2 decrements when we get to this point. So if you look at just doubling until you get to this point, look at this difference. So that difference is 17. Come up with a power of 2 that is closest to this. So 16 is really close to this 17. If you're doubling that many times before you start, then you can calculate. So 2 to what power is 16? 4.
Yeah.
If we look back 1, 2, 3, 4, then we can figure out that we can do the equivalent of 16 decrements here with 1 decrement here. So going from 3 to 2 is the equivalent of subtracting 16 at that point. And when you see something here that's relatively close to a power of 2, recognizing that when we double from 2, we go to 4, then 8, then 16, then 32, then we just have one thing left, a single decrement to do here to get to the 31. So it has to do with the greedy approach, as close to a greedy approach as we can get, is double until you go over, and then try to subtract based on a power of 2. That tells you where to insert that when we go back to this process. Where do you insert your decrements?
Got it.
That's as close to a 1 minute answer as I can give, I think. If you'd like to explore this in more detail, I have office hours, so I'd be happy to talk you through it. But that's at least mathematically the way that I view the problem.
Yeah. I don't know about security laws on it. I wanna work on it, see. See if we'll probably get that guy. But I can sneak some. Pretty sure a lot of people are getting so warm in your office. We'll see. Honestly speaking, I literally just met with one of my coworkers at protein meeting last night that I one day have to do 10 push-ups and vice versa, that one. So I think some have